Okay, here we go. Now we want to begin flow calculations, and we're going to have some specific objectives in this lesson. First, we want to explain Bernoulli's principle and describe the relationship between flow and a pressure drop. We want to define volumetric flow measurement as well as mass flow measurement. We want to be able to compare and compute flow measurements using the metric system versus the English system. Technically, the metric system is called System International, and the English system is called Imperial System, and be able to compute and convert between each one of those. And we want to be able to perform various calculations in either volumetric or flow, given specific process characteristics. So let's look at flow and differential pressure and relationship. So what I have here is a depiction of a section of pipe, and we have down here a differential pressure transducer, and you see I'm measuring pressure on two different locations on the pipe. And what this is called an orifice plate that is in the middle of the pipe, and it actually gives us an obstruction in the flow. And what the purpose of that obstruction is to give us a pressure drop across the obstruction that we can then infer the flow that is going through that pipe. So if I have flow going from left to right here, I will have high pressure on the left side and low pressure on the right side. And that's why we use a differential pressure measurement, and we can actually do some calculations based on the pressure difference across that orifice plate and be able to determine the flow. And the Bernoulli principle shows, this is a scientist found this relationship, that as the flow increases through the orifice plate, the differential pressure across the orifice plate will increase by the square of the flow. So if I go from 1 gallon per minute to 2 gallons per minute, the resulting differential pressure across there will have gained in magnitude a square of that difference. And that's why we no longer have a straight line. Now we have this curve, and this curve is basically taking this value and squaring it to give us that value. So that's why at the end here, 10 squared is 100, so that's why we're ending at 100 here at that point. Okay, 9 squared is 81, that's why it's roughly in that area, and so forth. Okay. So the differential pressure is whatever flow is going through it squared. Okay. So if we know the differential pressure, we take the square root of that differential pressure, and that will give us the flow. And we'll perform some calculations here. So here's an example. Let's take a pipe that has an orifice plate in it and put a differential pressure transducer across it, and has the orifice plate, and we're going to measure the flow based on our differential pressure. So the input range of the differential pressure cell that we have there is 20 to 100 inches of water column, and the output range is 4 to 20 milliamps. Okay. If the input is 30 inches of water, what is the output in milliamps after we do our square root extraction? Okay. So our first formula is a simple one that we've been used to. The span of our differential pressure is just our upper range value subtracted by the lower range value. And in this case, we have 100 minus 20, which gives us a span of 80 inches of water. And we're going to need that for this calculation. So we're going to take the whatever value that we get and subtract it from the low range value, because remember, 30 inches of water column is how far we've moved from 20. So we've actually only moved 10 inches of water column in our specific span. So that's what this numerator is giving us here. And then we want to divide that by the span, the total length that this could be measuring. And what that's going to give us is the percentage that we are within that span. And now normally we would just take that percentage if it was linear and then multiply it times our output range. But we're using square root, what's called square root extraction on this, because that's the relationship. We no longer have a linear transfer function. Now we have a square root transfer function. So we have to take the square root of that differential pressure percent. And when we take the square root of that, we get this 0.354 or 35.4%. That is what percentage of the range on the output that we are going to be operating in. So that's the first step in us figuring out what our output is. Now we have to figure out the span of the output. You probably have this memorized, but we just went ahead and did the formula here. If you take the upper range value minus the lower range value, 20 minus 40 milliamps is going to give us our 16 milliamps, and then we just multiply that times our square root extracted percentage, and that will give us where we are in the span. And again, remember, we haven't moved from 0 to that percentage, so we have to add back in the low range value of our 4 milliamps. So if we take our 35.4%, multiply it times our 16 milliamps, and then add back in our low range value, we are going to get a output from this transducer of 9.66 milliamps for an input of 30 inches of water. Okay, so let's look at another example, and we're going to calculate backwards forwards. So in this case, we're going to have a differential pressure cell across an orifice plate, but the range is going to be a little different. It's going to be 10 to 100 inches of water, and the output's going to stay the same, but the given information is going to be, if the transmitter is sending 8 milliamps of output, what should we expect the differential pressure to be across that orifice plate in inches of water? So let's figure out how we can back calculate that. So again, we're going to get our span of our output first, and then before, remember, we took the square root of the differential pressure, because remember, it varies with as a square of the flow through the pipe. So we had to take the square root. Now this is going the other way. We have to figure out what it is in relationship to what we're outputting. What we're outputting, we've removed the square root extraction, so we have to multiply it back in here by taking the square of that percentage of the milliamp output. So right here, we're figuring out the milliamp output of the differential pressure transmitter, and we're squaring it. So here's our range. Of course, we have to figure out how far we've traveled from our low range value. That's why 8 minus 4 milliamps tells us what we've traveled, a total of 4 milliamps within the span. Divided by the span, that's going to give us our percentage of the output. And of course, we have to square that, because that's the relationship between flow and our differential pressure. And that gives us 0.0625 or 6.25% of our range on our differential pressure cell. So then all we have to do is take that range and take that percentage and multiply it by our range. We know that we have a range of 90 inches of water, and so we just take that squared percentage that we had, multiply it times our span, and add back in our low range value to find that we have a differential pressure with that particular output of 8 milliamps as 15.625 inches of water. Okay, so let's talk about volumetric flow. So remember, this is the slide form factor for definition. And so volumetric flow is the rate at which a particular volume of fluid passes through a given point per unit time. Fancy way of saying that we're measuring usually in this country in gallons per minute. So this animation here that I have showing is if we just had a garden hose that had a certain volume coming out of it and we timed it with our watch. Well, if those are seconds, that would be 60 seconds to fill up the bucket. That would be 1 gallon per minute. And a gallon is a volumetric measurement. Okay, so if this is water, we could determine how much that would weigh. But if it is something other than water, if we're pumping alcohol or gasoline or something like that, volumetric flow doesn't really take that into consideration. It's just taking into consideration how much space of that liquid you're moving per a unit time. Okay, so that's our definition for volumetric flow. So in this example, 1 gallon of fluid passes through the garden hose in 1 minute, and this flow rate would be quantified as 1 gallon per minute, or GPM. Now, conversely, mass flow rate does not concern itself with the volume of water that you're moving. It's concerned with the weight of the water. Mass is a form of weight. So mass flow is the rate of a particular mass of fluid passing through a particular point in time. And mass fluid measurement is used specifically when the density of the fluid that is being moved changes. So if we are initially pumping water and then all of a sudden we start injecting in antifreeze into the water, we're going to be changing the specific gravity of the water and the viscosity. And when we do that, that means its mass will change. And so we use mass flow instead to understand the differences in the specific gravity of what we're pumping, and it gives us a better measurement, flow measurement, than we would with just volumetric flow. So in this little depiction here, what I'm showing is I'm not necessarily worried about the volume. I know I'm still filling a 1 gallon bucket here, but after a minute, I have moved 8.4 pounds of medium. It just so happens that a gallon of water weighs 8.33 pounds. So if this is purely water, then I am going to, every minute, if I have 1 gallon per minute of volumetric flow, I'm going to have 8.33 pounds per minute of mass flow. Okay. Now, if I start adding salt into this water, then the poundage is going to go up, which I believe I show in the next example here. In this example, the weight of 1 gallon passes through the garden hose in 1 minute. Okay. So this could be quantified as 8.33 specifically pounds per minute. Okay, so here's the comparison of mass flow versus volumetric flow. So in the left here, we have salt water. The volumetric flow, if we changed from pure water to pumping salt water, it's not going to be detected in volumetric flow because we're just measuring the amount of area that we're pumping per unit time, typically gallons per minute. So the specific gravity or the viscosity of what we're pumping is not going to be a factor. So the change in density will not change the volumetric flow rate. But if we are measuring in mass flow, and some flow meters can actually measure both at the same time, the change in density will change the mass flow. So in this case, I've said that these are both salt water. And if you notice the weight of what I'm pumping, we'll just say that these are both 1 gallon per minute. The weight of what I'm pumping has gotten higher because it has salt in it. So my mass flow rate will change with the changing density. Okay, so the density increased, but we still have 1 gallon per minute, and here the density increased, and so did our mass flow rate in our example to the right. Okay, so we have two measurement systems, right? We have System International, and we have Imperial. Imperial is still what we're using in this country. We still use the foot, pound, Fahrenheit in gallons. So flow rate, we most often talk about gallons per minute or gallons per hour, where in the metric system, we're going to talk about liters per minute, or we might talk about cubic meters per second or something like that. So there are two different measurement systems, and we're going to look at some examples of converting them. So in the imperial system, volumetric flow is going to be gallons per minute, but it could also be cubic feet per minute per second. All of these, the unit of time could change. So I say gallon per minute here, but it could be gallons per hour, gallons per second. And cubic feet per second is another way that often when we talk about air, moving air through big air handler, we're talking about cubic feet instead of gallons, because we typically don't measure air in gallons. On the mass flow side, we're going to be talking about pounds per minute or pounds per hour. That's going to typically be our measurement units. On the System International side, we're going to be talking about liters per minute or cubic meters per second. Again, that is probably a liquid versus a gas measurement. And then on the mass side, we're going to be talking about kilograms per minute. So that just gives you kind of an example of what you might see if you see those in the two different systems. Let's do some calculations. This is for volumetric flow rate. So this formula right here, we use just simple letters to represent kind of a longer English explanation. So when you first look at this formula, you might say, what's the funny V with the dot underneath it? It's just a new letter that we're going to use to represent something. It's not to get your eyes to glaze over and have you worry about what the formula is. It only has 3 terms in this entire equation. And once we understand the terms, it'll really drastically simplify the formula. So V dot, that's how you say that letter, V dot equals A times V, where V dot is just our volumetric flow, and A is area, and V is velocity, how fast it is moving. Okay. So let's look at an example here. This is very similar to one of your homework questions, but a drainage ditch has a 4 feet wide and 2 feet high affluent flow flowing through it at a velocity of 3 feet per minute. Calculate the volumetric flow. Remember, volumetric flow is just the amount of volume that we're moving through there. Okay, so to help picture this in your mind, I have a little graphic here down on the right-hand side that shows a cubic foot of water, which is a measurement, or I guess I called it an effluent. It doesn't have to necessarily be water. It could be, if it's a ditch, it's probably something other than water. But we have a width and a height, and then the velocity that's moving through there is going to give us our depth, and that's how we can get a volume for our volumetric flow. And of course, the rate, in this case it's per minute, is going to give us our time component as well. So let's look at the formula again. It's V dot equals area times our velocity. So the area of a rectangle is simply just the width times the height. Okay, so in this case, the givens were 4 feet wide and 2 feet high. The actual example said depth, but height and depth is the same linear measurement. And that's going to give us 8 square feet. Okay, so that is the surface area of that drainage ditch. And then we know that the velocity is 3 feet per minute. So all we have to do is multiply those two numbers together, and that will give us our volumetric flow rate. So if you notice, I'm taking feet squared times feet. That gives me feet cubed, and 8 times 3 is 24. So we're moving through volumetrically in that drainage ditch of 24 cubic feet per minute is what is actually flowing through there. Okay, so kind of a hairy looking formula at first, turned out to be fairly simplistic in calculation. Now the area doesn't always have to be rectangular. It could be of a pipe. So we have to use a different area formula for this. So water flowing through a 3-foot pipe, 3 foot meaning 3 foot in diameter, at a velocity of 15 feet per second, calculate the volumetric flow rate. Okay, so again, we have our V dot equals our area times our velocity, but we have a different formula for area, and the area of a circle is pi r squared. Okay, so we're going to take our 3-foot circle, and we are going to, now 3 foot is the diameter, and technically the formula for a radius is half the diameter, so that's why we have 3 feet divided by 2 to get it to a radius, and then we square it and multiply that times our simplified value for pi of 3.14, and we get 2.25 feet squared. Okay. Then we know that we have a velocity of 15 feet per second, and that, using our formula, is going to give us 9 cubic feet. Actually, that should be, I'm sorry, no, it's right. So we have 2.25 cubic feet times our 15 feet per second. That's going to give us 0.15 cubic feet per second. But we want to convert that to minutes because we want to know the volumetric flow rate in something that is more standard. So I'm going to take that 0.15 feet per second and multiply it times 60 seconds per minute. And you can see that the seconds on the denominator here and the seconds on the numerator will cancel out, and we're going to wind up with cubic feet per minute. So we wind up with 9 cubic feet per minute in this example. And here's just the graphic of what we're doing. So we have the velocity coming through here of 15 feet per second, and our diameter, which is how pipe is defined. If you say you have a 3-foot pipe, that's the diameter. I had to convert that to the radius by just taking the diameter and dividing it by 2. And now we know the volumetric flow rate going through that pipe is 9 feet cubed per minute. Okay, mass flow rate. Here is our formula for mass flow rate. And we have a little bit of a different formula. So the first term there is m dot, and m dot is our mass flow rate. And of course we know v dot now is volumetric flow rate. And p, we learned, well, I shouldn't say p. That's the Greek letter rho, looks like p. The Greek letter rho symbolizes density. We learned that a couple units ago. So all we're doing here is taking our volumetric flow rate, and we're taking the density of the material being pumped into consideration, because that's going to make it the mass flow rate change. So a liquid has a volumetric flow rate of 20 cubic meters per second. Okay, so we're in the System International units here, and a density of 0.5 kilograms per cubic meter. Calculate the mass flow rate. So we have a something that is being pumped. We don't know whether it's water or what, but we are trying to figure out per, in this case, second, what it is, what mass is flowing through there. So let's use our formula. M dot equals V dot times rho. So our volumetric flow rate is a given. It's 25 cubic meters per second. And our density is also given. It's 0.5 kilograms per cubic meter. So all we have to do is just plug those right into our formula. So m dot, or our mass flow rate, is going to be 20 cubic meters per second times our 0.5 kilograms per cubic meter. That gives us 10 kilograms per second. And if we want to convert that to minutes, we could. I don't believe I did that here on the slide. But we know the formula for that. A liquid has a volumetric flow rate of 15 cubic feet per second and a mass flow rate of 1,000 pounds per second. Calculate the density. So here we're lucky. They're both given in the same time units. But if we know the volumetric flow rate and we know the mass flow rate, all we have to do is transpose our mass flow rate formula, and we can figure out our density. So this is our mass flow rate formula. If we transpose it by dividing V dot from both sides of the equation, we're going to get rho equals m dot over V dot. And then we just take our givens our givens, we're trying to figure out what our density is in this case. Our givens are 100 pounds per second, and for our mass flow rate, and our volumetric flow rate is 15 cubic feet per second. And all we have to do is put that into the formula, and we get 66.67 pounds per cubic feet. Okay, so we know that that is going to be a little bit heavier than water. Okay. Okay, so let's look at another example here. Water is flowing through a pipe at 15 gallons per minute. Calculate the mass flow rate. Okay, so you say, I don't have enough givens there. Well, you actually do. It says water is flowing through the pipe. So we know the density of water, or we can obtain that. So the rho of water, or the density of water, is 8.33 pounds per gallon. Okay, and now we know that we have 15 gallons per minute. Then it's just simply plugging it into the formula. So we have our formula: mass flow rate equals volumetric flow rate times our density. Mass flow rate is 15 gallons per minute. Our density is 8.33 pounds per gallon. And we just do the math there. 15 times the 8.33 gives us 124.95 pounds per minute. Okay, so that is our mass flow rate of water at 15 gallons per minute volumetric flow rate. Okay, so now let's look at another conversion for a drainage ditch. And this one has a width and a depth. Depth and height, again, are the same linear measurement of 3 by 3 with the effluent flowing through it at a velocity of 15 feet per minute and a mass flow rate of 5,000 pounds per minute. We want to calculate the density of the effluent. So if this truly is a drainage ditch, this is actually a very common thing that we do in the field. If you're getting rid of a solvent by draining it, and that the density is changing all the time, there's ways that we could use the physical area and the mass flow rate and the velocity to figure out the density of what's going through there, and making sure that we're not putting too dense of a material into a drainage ditch. Okay, so our volumetric flow rate is going to be our area times our velocity. So our area, again, is just height times, in this case, depth, which gives us 9 square feet. And our volumetric flow rate is given at 5 feet per minute. So our volumetric flow rate is going to be 45 cubic feet per minute. Okay, but we want to calculate the density of this. So we're going to use that volumetric flow rate and with the mass flow rate to figure out the density. So we have to transpose our mass flow rate formula to get rho on the left side, and our mass flow rate over our volumetric flow rate is going to equal our density. So we're going to take our mass flow rate of 5,000 pounds per minute and our volumetric flow rate of 45 cubic feet per minute. And now it's important in this formula that you keep the time units the same, and also we're using the same measurement system. So I'm using the imperial system here for both pounds and feet. You wouldn't want to use like kilograms and feet, or pounds and meters. Okay, so we have 5,000 pounds per second divided by our 45 cubic feet per second. And that's the same formula as having 5,000 over my 45 cubic feet per second. And that gives us 111.11 pounds per cubic feet. Okay, so that's the density of the effluent that's moving through the through that drainage ditch. And it could be in the field that there is a target, maybe from the EPA, that the density does not get above too high of a specific measurement, or you get fined. So that's a very common thing that we do in the field, in the chemical industry specifically, to make sure that we're not putting too dense of liquid into a drainage system. So that concludes our formulas for our flow unit. I hope that helps, and we'll see you in the next video.